Right, it's gone, so we can continue. Now, in an example, oops. Oh, we know. So what just happened? I will have to redo all of that. What? And what happened just happened. So we just have to redo the whole thing. Oh. Somehow last time it didn't ask us that question. All right, can you guys hear me? Okay. Well, unfortunately, when it went live, I clicked on the wrong button. Everything just went away. So hopefully it will not happen again today. So example here, A, in the case of equiprobability, which means when the elementary outcomes have the same probability, so if probabilities are computed under the assumption that the event C has already occurred, and NC is the number of outcomes in C, then the probability of any event A given C, this is the notation, the probability of any event C given that the event C, of any event A given that the event C has already occurred is equal to N AC over NC, where N AC is the number of events, the number of outcomes, sorry, in A and C. So again, let me go back. In the case of equiprobability, if probabilities are computed under the assumption that the event C has already occurred and NC is the number of outcomes in C, then the probability of any event A given C, so the bar here means given, is equal to NAC over NC, where NAC is the number of outcomes in A and C, which means the number of outcomes, the number of outcomes that are both in the event C and in the event A, the intersection of the two events. And NC is already defined here, the number of outcomes in C. In the example of a die that we cast, NC was 3. If given that the number that fell is even, NC is 3 because the even numbers are 2, 4, and 6. 3 of them. And now probability that the number is 2, that means 1 out of the 3 numbers. How many events are actually for 2? Just one, right? Only one outcome is 2. So that's the only number that is there is 2, and the intersection of that set that is only 2 and 2, 4, 6 is 2. So one number. So there's one number here representing NAC divided by NC in that case, which is 3. So 1/3. So now in general, this gives, if you don't have the numbers and you have the probabilities, this gives the probability, the formula, probability of A given C equals P of A and C divided by the probability of C. So if you condition on C and you have the probabilities instead of the outcomes, what you need to do is to take the probability of the intersection of any event with C and divide by the probability of C. Therefore, you will get the probability of A given that the event C has already occurred. So notice that if S, which is the sample space, is equal to S, let's divide this S1, S2, S3, all the way to SK, and SI intersection with SJ is empty for any I and J. So if you can split the sample space into K disjoint subsets, then the probability of S given C, on one side it is 1 because S is the entire sample space, right? Given any event, the probability of the entire space is 1. And that is going to be equal to the probability of S intersection with C divided by the probability of C. And because S is a union of disjoint sets, this is going to be probability of S1 and C plus all the way to SK and C, right? Because the sets are disjoint. That's the same property we used last time to prove all the theorems that we had. Because these sets are disjoint, that top can be written like this. Divide by P of C. And notice that this is probability of S1 given C plus probability of S2 given C, and so on, Sk given C. So when you condition on C, all the rules of probability remain true. So the conditional probability given C is actually also a probability function. All the rules that apply to the probabilities that we used last time will apply to the conditional probability given C because of this. Any questions on this? After this, we'll use it to solve some problems if you see that. Is there any question? Right. Is empty equal to the null set. Now, second part here would be what we call the law of total probability. So in most problems, the sample space splits as in the last formula that I gave you into a union of disjoint sets like that. Okay, so that's what this one is also about. So let's say we assume S is S1 union S2, and then all the way to Sk, and Si intersection Sj is empty for all Ij. If that is true, then for any event A, the probability of A is equal to A intersection with S1 union, and you take that union all the way up to A intersection with Sk. That will be true because the event A is either in S1 or in S2 or in S3 or in Sk or partially in each of them, right? And because Si intersection with Sj is empty, the intersection of any two of these sets is going to be empty. Therefore, the probability of A is equal to the probability of A intersection with S1 plus probability of A intersection with S2 all the way to A intersection with Sk. And because that is true, we can use the conditional probability because often in this case, we know the probabilities of having the sub-sample spaces, the S1, S2 up to Fk, we know their probabilities. For instance, if we have, say, a company has 5 plants that are producing, and he knows the probability that an item that is found in the market comes from each of the plants, right? He knows that probability because he knows how many items are produced in each of the plants. And now he wants to have some inference on what is happening on the market with the products, knowing, for instance, where the bad items stocks mostly progress. So he might want to use this to figure out if an item that is on the market is defective, where is it coming from? What's the chance that it comes from the first plant or the second or the third and so on? So here, because we know these probabilities, we can use the conditional probability. So that is A given S1 times probability of S1, which is known. And usually this can also be found because if I am already at the plant number 1, the people that are in charge of that know approximately the quantity of items that are defective at their plant. Does that make sense? Because there is somebody there that is in charge of quality. Right? Then at the second plant, it's the same thing. A given S2 times the probability of S2. And so on, all the way to probability of A given Sk times the probability of Sk. So for example, if that was a defective item that I found on the market, I want to find if I get an item on the market, I want to find the probability that that item is defective, for example. I know it can be defective coming from the first plant times the probability of the first plant. It can be defective coming from the second times the probability of the second. It can be defective coming from the K times the probability of the K. Does that make sense? So this formula is called the law of total probability. So this is what we call the law of total probability. And that formula is usually going hand in hand with the next one, which is called the Bayes rule. In which the opposite question is being asked, the one I was asking earlier. If I found a defective item on the market, what is the chance that it comes from plant 1? If I found an item defective on the market, what's the chance that it comes from plant 2? And to answer that question, we use this next formula, which is called the Bayes rule. So probability of Si given A. So given that the item that I found is defective, what's the chance that it comes from Si? And we use first the definition. That's probability that it comes from Si and it is defective, divided by the probability that it is defective. Do we agree? That's the definition, right, of conditional probability. And now you use this formula, the law of total probability, to find P of A. That's what goes down. So we say that it's P of A given S1 times P of S1 plus P of A given Sk times P of Sk. That's P of A using the law of total probability. And then on top, you use the conditional probability of A given Si times probability of Si. Remember that the setup tells you that you know the chance of being at a given plant, and at each of the plants, you know the chance of having a defective item. And this formula gives you the probability that an item is defective, that the defective item comes from the planets are, even you know already that it is defective. And this is what we call the bias formula. And you can see it just comes from that ratio, which is the definition of the conditional probability, to which we added the law of probability. So examples, the exercise. Company has 3 plants, C1, C2, and C3. It is known that the C1 produces 10%, E2 produces 50%, and C3 produces 40% of the company's stock. The quality engineers declare that, oh, sorry, 1% of the production at plant C1 is defective. 3% at plant C2 is defective, and 4% is defective at plant C3. An item of the company is randomly selected. One, what is the probability that it is defective? And two, given that it is defective, what is the chance? What is the probability that it can from C1 to C2 separately? So what's the chance that that defective the item came from each of the plant separate. So these two questions use everything that I talked about from the beginning. How do we answer it? So we have a company that has three plants, C1, C2, and C3. It's known that C1 produces 10%, C2 50%, C3 40% of the company's stock. The quality engineers declare that 1% at plant 1 are defective, 3% at plant 2, and 4% at plant 3 are defective. And then we got an item from this company. What's the probability that it is defective? 1. And 2, given that it is defective, what is the probability that it came from C1, C2, or C3? Again. All right, so answer. How to answer this question? First, I'll say D. We define the event D, which means the item is defective. And CI, that the item is from the plant CI. And so the first question is asking us, what's the probability of D? What's the probability that it is defective? That's the law of probability, correct? Because we know the sample space in this case splits into 3 parts, and we know what happens at each of the parts, right? That's why you know it's the law of probability. We have C1 separately, C2 separately, C3 separately. Things are happening there, and we want to combine them. So that is going to be P of D given C1 times P of C1 plus P of D given C2 times P of C2 plus P of D given C3 times P of C3. And these are all the things that we need. We need 6 numbers. Where do we find those 6 numbers? From the problem. The problem says 10% is produced at C1. So what is the chance that an item comes from C1? 0.1. That's it. So you turn the percentages into probabilities. So P of C1 equals 0.1. P of C2, the problem says for 50% at plant 2. So that is 0.5. And P of C3, it says 40% at plant 3. So that is 0.4. Now, the conditional probabilities, you need to make sure you understand them. P of D given C1, what is it? Just in words first. What is P of D given C1 in words? The probability that an event, that an item is defective, knowing that we are at plant 1. So the most important thing in those things is to be able first to get away from the mathematics and get the English version of what you're trying to ask. Because often people have the mistake of thinking that P of A and B is in place of P of A given B, depending on the word. And your problems will be in words. And you will have to go from the words to form. And often what happens is instead of writing the conditional probability, people write the intersection. So here, given that we had plan one, it's the engineer at plan one that said you have 1% defective. So that's 0.01. Because he knows only what happens at plan one. P of B given C2, they said it's 3%, so that's 0.03. And P of B given C3, they said it's 4%, so that's 0.04. That's it. Now you have all the 6 numbers that you need for that formula to work with. Therefore, P of B is 0.1 times 0.01 plus 0.5 times 0.03 plus 0.4 times 0.04. Does it make sense? Then you have the second question. What's probability of C1 given B? That's given that the item is defective, what is the probability that it came from C1? And here is where you have the base formula. If we didn't answer the first question, we would just write down the base formula and have it. But because we answered the first one, we just do the probability of the intersection divided by the probability of B, which we already have. Right? So that's probability of C1 and B over probability of B. I know this already, so I don't need to take probability of B back into that again to redo it. So, but the top, I know it's probability of B given C1 times probability of C1. I know probability of B given C1, it's right here. I know probability of C1, it's right here. Over probability of B, which I already computed. So that is going to be 0.1 times 0.01 over whatever this is. Could anybody compute that? Yeah. So, and then you do the same thing for C2 given D. For C2 given D, it's going to be 0.5 times 0.03 over that same denominator. And then for C3 given D, you will take the numbers for C3. That's it. Any questions about this? That's how we use the definition of conditional probability, the bias rule, and the law of total probability. next part is independent. We say that two events, and this is a very important concept in statistics, allows many things. When you don't have independence, then life is a little more difficult. We say that two events, A and B, are independent if and only if probability of A given B equals probability of A, or probability of B given A equals probability of B. Which means what? That two events are independent if knowing one doesn't affect the other one. Does that make sense? Which is very different from disjoint, which we had last time. In fact, if two events are disjoint, they can be independent. What is the intersection in the disjoint? Zero. Empty set. And what's the probability of the empty set? Zero. So the probability of their intersection is zero. Now, this definition is equivalent to saying that the probability of A and B equal the probability of A times the probability of B. Which is the reason why if they are disjoint and none of them is empty, then they cannot be independent because the probability of the intersection is zero. Are you there? All right. Second part, we say that A, B, C are mutually independent if and only if they are pairwise independent. Pairwise meaning what? That if you take any two of them, they are independent. Okay. If you take any two of the three, they are independent. So we say that A, B, and C are independent just without the word mutual. As if and only if P of A, B, and C is P of A, P of B, P of C. And that's not the same as controlling. So this mutually independent doesn't imply independent. Independent implies mutually. Meaning that there are cases when you have three events that are independent two by two, but the three of them, for the three of them, this equality is not satisfied. But anytime this one is satisfied, that condition is satisfied as well. So, does anyone have a book here? The book for the class? Did anyone bring it? And if you have the P there, it's fine. I just want to know if you have it here because I want somebody to read for me. I don't know how to read English, so I want someone to read for me. So page 28, problem number 1.4.9. Mm-hmm. 1.4.9. Oh, let's read it first. Page 28. What's the version of the book we have? Maybe we have a different. Yes, version, edition. That doesn't count. It's the 6th edition. So if you have that one, you need to make sure you get the proper problems because the problems are assigned from the book and you will have the wrong number. It's the 6th edition that we use. The 7th edition that we use. All right, so anyway, let me try to read it then. So please don't laugh, okay? So, does anyone want to read it for me? They are just smiling, all of them just smiling. All right. Ball 1 contains 6 red chips and 4 blue. Who likes the chips? So we have ball 1, which contains 6 red and 4 blue. Let's forget about the chips. Just say red and blue. Okay. 5 of these 10 are selected at random without replacement to put in ball 2, which was originally empty. So ball 2 is empty. And from the 10 shapes, randomly without replacement, we select 5. So from these, select 5. When you select 5, put them in all 2. So now here we have 5, and we don't know the color. because they were randomly selected from ball 1. Does that make sense? So in ball 1, we have 6 red and 4 blue. We randomly select 5 and put in the empty ball 2. We don't know now what are the colors that are in there. Then, this is the experiment now. One chip is then drawn at random from ball 2. So now, from here, select 1. Given that this chip is blue, find the conditional probability that 2 red chips and 3 blue chips are transferred from ball 1 to ball 2. What's the number in your book? 8? You see what how to change it, right? So be very careful. So now we want to know, we select 1 here, and that one is, what did they say? Blue. So we select 1 and we figure that this one is blue. And we want to know what is the probability that we selected here, this selection. What's the probability that we selected 2 red and 3 blue, given that we got the blue at the end. So, does everybody see the setup of the problem? What do you think? How do we answer this question? So the problem starts in ball 1, in which we have 10 balls, 6 red and 4 blue. We randomly select 5 and put into another ball. And then from there, we select 1, and we realize that the one that we selected is blue. What is the chance that initially we selected 2 reds and 3 blues to put in there? That's the question. What does it look like? What do we need to use here? Base. Why? Because we are conditioning on the result. We are conditioning on the result of the experiment. So we need to use base form. Am I making sense? So anytime you're conditioning on the result of the experiment, you think of base formula. And why will it be actually the full base formula here? Because the sample space here splits into a number of parts that we still need to determine. Because we don't know the composition of the 5 balls, so the chips that we are taking here. That could be 1 red and 4 blue, 2 reds and 3 blue, 3 reds and 2 blues, 4 reds and 1 blue, 5 reds in it. So that's where the subdivision of the sample space comes. And you need to find the probabilities for every single case and take them all together to get the answer that we're looking for. Does that make sense? All right, so solution. We start by here, omega. Let me call it S as I used to. Is we put all the options that we could select here. That's the subdivisions of S. That could be 5 red. We could select 5 red. Could we select 6 red? No, because we are taking 5 chips. We can't get 6. So it could be case 1, 5 reds. Case 2, 4 reds, 1 blue. That's case 2. Then 3 reds, 2 blue. That's case 3. Then 2 reds, 3 blue. That's case 4. Then 1 red, 4 blue. That case 5. Could we have 5 blues? No, because we don't have up to 5. So the sample space splits into 1, 2, 3, 4, 5 disjoint sets. Because this is not here. This case is not here. The intersection of any two of them is empty. Does that make sense? All right. So now, what is the probability of C1? The cases that I have. What's the probability of selecting 5 reds here out of the 10 balls? From 10 balls, we are selecting 5. What is the probability that they are all 5 reds? Remember what we did at the end of the previous lecture? These are the counting, right? The counting principles. We are selecting 5 balls at the same time without replacement. So what formula needs to be used? 5 choose. So we are choosing 5 out of 10. That's another notation for that. And here we are choosing 5 out of 6. So the number of cases here is choose the 5 out of the 6 red, because we have 6 red. And the total number of elements in the sample space is choose 5 out of 10, because we have 10 chips from which we are selecting 5 without replacement. All right. And so that's P of C1. What's P of C2? The denominator doesn't change, right? And what's the numerator? How could I select 4 reds and 1 blue? Select 4 reds. How many reds? 6. And select 1 blue out of. Are we together? Out of 4. And that is multiplied, because that's a product rule. You're selecting the reds and then you're completing by a blue. Please, if you have a problem, stop now, because this is the time to get it. We are not adding because we need to get 5 of them. So here we just have 4. We need 1 more. So that's why we are multiplying. Because for every 4 reds, I need 1 blue. Then, what's the probability of C3? That will be choose 3 out of 6. Then complete with 2 out of 4. And the denominator still doesn't change. P of C4 will be choose 2 out of 6, then choose 3 out of 4. And the denominator is the same. Then you have P of C5, which is choose 1 red out of 6, and then choose 4 out of the 4 blue. And the denominator is still the same. So this is the chance of having separately each of the portions of the sample space. Now we need to find the conditional probabilities now. Given each of the cases, what is the probability to get a blue? Right? So what is probability of B given C1? Given C1, if C1 means what? Select 5 reds. If I selected 5 red to put on in ball 2, what is the probability to select a blue from there? 0, because there is no blue there. Okay. So, do you agree with this? Given C1, we know the sample space now is C1. What's the chance to have a blue here? C1 means select 5 reds and put there. So there is no blue. There are 5 reds there. So the probability is 0. The probability of blue given C2. C2 is take 4 reds and 1 blue, put in there. So right here, I have 5 balls of which 4 are red, 1 blue. What's the probability of having a blue? 1/5, because there are 5 and 1 is blue. 1/5. Probability of B given C3. What is it? C3 says take 3 reds and 2 blues and put in there and select 1. I have 3 blues and 3 reds and 2 blues. What's the chance of having a blue? 2/5. Does everybody follow? 2 out of the 5. What's the probability of B given C4? Given C4, and C4 says 2 reds and 3 blues. What's the chance of getting a blue? 3/5, because there are 3 blues. And then the 5th case, P of B given C5 equals how much? 4/5. So in that case, you get 4/5. So these are all the numbers that we need. So we have all of them now, and now we can write the formula. What was the question again asking us? That again. Red. What's the point? That 2 reds and 3 blues. So 2 reds and 3 blues. That's probability of C4 given B, right? So you need to be able to use the language to write down the answer. So this is what we need. That's the question. What's the probability of C4 given that we got the blue? And by the bias rule, that is equal to P of blue given C4 times probability of C4 divided by the sum of probability of B given C1, P of C1, plus probability of B given C2 times P of C2, plus probability of B given C3 times P of C3, all the way probability of B given C4, P of C4, and probability of B given C5 times P of C5. And now you can check, we have all the necessary numbers. P of B given C4, we have it. P of C4, we have it. And all these probabilities we have, and you just take those numbers and plug in. Question? Does it look scary? But you understand that if you are following the principles, and it is really easy. And the good thing is about this is that you need to understand the wording of the problem. Yes. Law of total probability. In the problem, for example, here, what leads to total probability is look at the problem. Get it back down here. When you draw this to answer the question, you see that you are selecting from here, but you don't know what is inside here. What is inside here depends on what comes from there. So you got to split. And if you got to split, you know it's total probability. Does that make sense? Now, what brings us to the bias rule? is right here. When you write down everything, you know that this is the outcome of the experiment. And anytime you write the formula and you see that the outcome of the experiment is on this side, right? Does that make sense? So the most important thing is to be able to write down the formula here, because that's what dictates everything. And unfortunately, I know some people never like to put down the formula. Start doing it. And if you don't, then it becomes more difficult because you want to guess things that would otherwise be easy if you just write down what you're looking for and then you remember your formula. Yeah. And for conditional probabilities, you need to know always if you have words like given, under this condition, under that condition, those things are calling for the conditional probability. Does that answer your question? Any other questions? Yes, sir. With replacement, when you have with replacement, here, for example, we could have 5 blue. If we are selecting with replacement, then there is one subcase that is added because we could have 5 blue. And we are not more using combinations because we are replacing. And you know what? When we do replacement, we need to use the multiplication rule. So this is going to be, instead of here, choose 5 out of 6, is going to be 6 to the power 5. Right? So everything changes if you go with replacement. Remember with what? It doesn't change. Everything else in the solution stays same. All that changes is the probabilities themselves, how you compute them, right? But the rest of the problem is solved exactly the same way. The way you select things affects only the individual probability. They don't affect the steps for solving the problem. They remain the same. The law of total probability will remain, the base rule will remain, but these probabilities that we found here will change. Other questions? I would love to solve more problems, but we are running out of time. We are only 1 minute left. And the most important thing with this is please don't wait. Answer questions. Answer questions. Yes, please. That's your homework. Homework 1. That's 1.3, problem 13 and 14. 1.4, problems 1, 8, 14. 1.5, problem 3. And these are other problems that I wanted to solve in class. If you have time to look at them, you can do 1.4. I solved 9. We still had 10, 11, and maybe 29, but I just didn't have time to solve all that. And 14. So if you're interested, you could do these ones also and send to me if you want me to do them. They are similar to the ones you solved. Huh? Homework due Wednesday. Wednesday. It's 1 week. Yes. So far, what we have covered is from 1.1 to 1.5. Any question? Yeah, you had a question. Someone was asking me a question before I put the problems on. Like what? What I post is the video of the class. It's nothing else. Thank you. Yeah. And if I am to take pictures of the notes and post, it's the same thing that you see on the video. That's on Blackboard. So they are on YouTube, and I post the link on Blackboard. So you can open on the content. Yes. Any other questions?
Can you read out the pages or the homework assignment again?
So that's homework. Problem is section 1.3, problems 13, 14. Section 1.4, problems 1, 8, and 14. Section 1.5, problems